Hey guys, so in this video I'm going to walk over some of the method of characteristic steps just so that make it easier for you to code and understand what's going on. So hopefully you guys had a good understanding of what we talked about in class today. I'm just going to continue on that. So in this slide, we understood that if you want a Mach number exit, a certain exit Mach number out of the nozzle, the maximum angle of deflection near the throat should be about Prandtl-Meyer function of that Mach number divided by 2. So that's what we saw in the class. And so to start the method of characteristics, what we do is we assume that the change in that angle happens gradually. I do wanted to show this slide again one more time, mainly because in the class I showed the first turn happens before the first Mach line, which is not the case. So here is, right. So here is the first Mach line. So after it crosses that Mach line, it turns about 0.3 and then so on and so forth. After the last Mach line, you should get a turn angle of about 18.3 degrees as we said. So now, that's I hope you understood until up to this part. So let's look at point by point. So let's look at the first point. Here's the first characteristic line. So we know that the theta1 and v1 can be given by this equation. Just know that since it's the first point, our C plus and C minus, or sorry, our C plus, which is basically the left running characteristics, is considered 0, right? So then you're just basically left with the C minus, and C minus A is theta A plus nu A. Now, from our class discussion today, I hope you guys understood why nu A is also equal to theta A, right? Because you have an inlet Mach number of 1, and by the time the float turns, we have to add the Prandtl-Meyer function of that Mach number, which is basically Mach 1 plus this theta, but Prandtl-Meyer function of the Mach number 1 is actually 0. So you end up getting theta as your Prandtl-Meyer function as well. So you get the theta as 0.375 degrees, and also from this equation you get the mu as well. So using the Prandtl-Meyer function, you can actually get the Mach angle at 0.1. So now using this equation, you can determine what the slope of A1 will be. So I hope you understood up to this point. So let's talk about point 2 from now. So in point 2, again, it's the same equation. It's half C minus plus C plus 1, right? So I hope you understood this. So I'm going over the first 2 steps a little bit faster because since we talked about this in class. Again, if you have any questions, just let me know. So here you have you're looking at point 2, so that means at the second Mach angle you get 3.375 instead of just 0.375. So that's all good. I'm gonna put that into the same equation, and you will get a theta 2 and mu 2 and the corresponding Mach angle at that point right there. So and then later we gotta calculate the slope. So slope is you get the slope of 1, 2. So here you have the left running characteristic line right here. So half of theta 1 plus theta 2, we know what theta 1 and theta 2 is, and we know what mu 1 and mu 2 is. So if you calculate that, it'll come to around 67.2 degrees. So then from A2, our second Mach line, right here, so this line, slope of this line, you can calculate the same way, but since this is a right running characteristic, we get a minus sign right here. So you get theta A plus theta 2 minus half mu A plus mu 2, which is basically that. So Now here's where we can generalize this concept, this step. All right. Now let's move on to point 3. So you use the same equations. Instead of +1 or c+1, you get c+2, because now you have to account for this point 2 to point 3, right? You get theta 3 and mu 3. C minus a is basically theta a plus nu a, and we know that theta a equals nu a because our exit or the entrance Mach number is 1. So we're considering third Mach lines, which is about like 6. That's why you get the 6.35. Okay, so now 3.35 is basically what you have at 2. So using the same equations, you'll end up getting a value for theta 3 and nu 3. And if you see, it's similar to what you get in what you have in Mach number Mach line 3, right? So now comes the slope, right? Once again, same equations. Similarly, you do this for 0.4, and then 0.5, and then 0.6. Nothing else changes. It's just the same equations overall. Okay, now how do we code this? You can actually see that the equations that we use are pretty much the same, right? So what I did initially is, I hope you guys can see. Let me check how much. All right. So I hope you guys can see this MATLAB window right here. Since this is a high definition video, you might want to view this in a 1020 pixels, so that you have good resolution. But just in case, I'm going to increase the size a little bit. There you go. All right. Let's look at that now. So what I did here is that in order to code this, I first started with just regular, code, just what we did in here. Say, let's start at point 2 because that's easier. At point 2, my theta a was 3.375, and my mu a was equal to theta a, right in here. And so this is the t that coming from, that's about the point 1, and I know that's 0.375, and similar to what you have about nu equals t, right? So I can find the Mach Mach angle at these conditions, right? So now here I program this equation. Basically, theta 2 is half. Well, no, before that I gotta find the c minus a and c plus a values. So c minus a, CMA is TA, theta a plus nu a right here. So then C plus is theta minus nu, which basically this equation right here. So now I need to find the nu theta, which is at our, I named this nu because that's our point of interest, point 2, right? And then n nu is the nu at the point of interest, okay? So this 0.5 times c minus a plus cp, 0.5 times c minus a minus cp, right? So I hope you guys can follow this. I'm basically coding these two equations in here, and I'm finding the corresponding Mach angle using this formula, right? So once I do that, then I can program the slope. So slope is basically half of theta 1, which is basically t in here, and t2, that's our reference points, that's our my theta nu, then mu t, mu nu, and so on and so forth, right? Now all I did is, I did for 3.375 at point 2, I'm getting all these values. So if I go to point 3, if I go to point 3, then my TA changes to 6.375, and my t goes to 3.375. Now if I run that, right, so now I'm getting exactly what you see in here. It's like my Mach angle is 49.8, my slope t is 58.3 minus my slope of the Mach angle is minus 43.5, right? So if I want to do 0.4, then I do 9 for A, and then theta, I reduce it by 3 degrees, and then I run it again. So that's 0.4 right here, right? Now I'm getting 35.6, 35.3, right? So now what we did here is we generalized this approach, right? We wrote a common code that could get values for all these data points right here. Okay, so in the next video, I'll show how you can even condense this even further and determine the wall location and also the XY coordinates. Okay, all right. Let's stop here and move. Let's if you're not sleepy by now, you can move on to the next video. Otherwise, just go back to sleep.